What if I told you that there exist ways to measure distance where the Euclidean rules don't hold? Or that you can measure distances between functions? And yet in all of the examples that follow, your most basic intuitions on distance still hold. Let me ask you this. If I tasked you with making a function that takes as an input 2 points in space and spits out the distance between them, what conditions would you impose on such a function? There are probably many that you could come up with, some more useful than others, and through trial and error, you may stumble upon combinations that give you desirable properties. Luckily, the bulk of the work has been done for us, and mathematicians have found that the following 3 axioms lead to some beautiful consequences. The distance between any 2 points should not be negative, and equality should be achieved if and only if we are measuring from a point to itself. This should be logical, since we think of a distance as a scalar value that measures the size of the gap between 2 points. We can also see that the only way 2 points are in the same position is when the distance between them is 0. The distance should also be independent of the way we measure. Whether we measure from x to y or from y to x, we should get the same result. In other words, the function should be symmetric, and the order in which we input the points shouldn't matter. The final axiom is that for any 3 points, say x, y, and z, the sum of the distance from x to y and then y to z should always be larger than measuring directly from x to z. This may seem a little more complex than the last 2 statements, but it really just captures the idea that the shortest measure of distance is always direct. It is of course possible to obtain equality, which in Euclidean space just means that y lies on the line segment between x and z. So what is a metric space? A metric space consists of a set x and a function d called a metric that satisfies the 3 metric axioms. With this, we now have the tools to tackle some examples. For this example, we can let x be any n-dimensional real space. This could correspond to the real line if n is 1, the real plane for n equals 2, or really any other number of dimensions. But for simplicity, let's look at the case where n equals 2. As a metric, we take the standard Euclidean metric, which takes the square root of the sum of the differences in each component. In 2 dimensions, this simplifies to the Pythagorean theorem where your a and b are the component-wise differences between the 2 points. Take again the real plane, but this time we define the Manhattan metric, which simply sums the absolute values of the differences in each component. Imagine you're in a city and you want to know the distance you need to travel between 2 points. You can't just cut across buildings, so the Euclidean metric doesn't hold. Instead, you need to travel along roads which are parallel to the axes. Then you get exactly the Manhattan metric. We remain on the real plane and define the discrete metric that equals 0 when measuring from a point to itself and 1 otherwise. This means that for any 2 distinct points, they're all the same distance apart. It essentially acts as a sort of indicator function that tells you if the points are equal or not. This is by far the weirdest example, but it serves as a good reminder that despite the intuitive nature of our axioms, we can still construct contrived and rather unintuitive examples. Take x to be the set of bounded functions on the interval 0, 1. There is no requirement on smoothness nor on continuity, so the functions in this set can be really quite ugly. We require only that the function can be bounded from above and below by a pair of real numbers. To measure distance, we take the Supremum metric, which returns the supremum of the difference between the 2 functions on the interval. This is especially useful when we care about the uniform behavior of functions. Now let's suppose we don't care so much about uniform behavior, but rather the average behavior of functions on the interval. then we can take x to be the set of continuous functions on 0, 1 and define the L1 metric as the integral of the absolute value of the difference between the two functions over the interval. The geometric interpretation is that it returns the total area between the two curves. Now notice that we didn't impose boundedness on our set of functions, and you would be thus correct to question if the L1 metric is even well defined. But fortunately, we have chosen our interval to be compact, so boundedness is ensured by continuity. Just like in real analysis, it is of fundamental interest what happens in the vicinity of a point, but this time, the vicinity depends on the chosen metric space. Let the pair xd be a metric space. Then an open ball around a point is essentially the set of all points within a fixed vicinity according to the metric. Recall the definition of an open ball. If we combine this with the Euclidean metric, we get the following. You may not immediately recognize this, but if we square both sides of the inequality, we see that it defines a circular disk around the point A of radius r. Notice that we use a dotted outline to emphasize that the border of the disk is not included in the set. Using the Manhattan metric for the open ball, we get an entirely different set, and for simplicity, let A be the origin so that the ball is centered at 0. Now to create this ball, we will begin by constructing its boundary, which is obtained by setting the metric equal to the radius. Then we look at each quadrant individually. In the first quadrant, x1 and x2 are positive. Therefore the absolute values have no effect and the sum must be equal to the radius. This gives us the following line. For the second quadrant, x1 is negative and x2 is positive. So the absolute value flips the sign of x1 and we get that the sum of negative x1 plus x2 is r. Treating the last two quadrants similarly gives us a drawing for the border, and so it is not difficult to see that the ball consists of all points contained in a diamond around the origin. With the already weird definition of the discrete metric, it is not a surprise that the discrete ball is also rather odd. We will get an understanding of the ball by increasing the radius and seeing what happens. When the radius is smaller than or equal to 1, the ball is simply our point A. But watch what happens when we increase the radius even slightly over 1. The ball suddenly takes up the entire real plane. Why is this? Well, if you look back at our definition for the discrete ball, all points distinct from A have a distance of 1 from A, with only A having a distance of 0. Thus, when the radius is smaller than or equal to 1, only A satisfies the condition. But as soon as the radius is larger than 1, all points on the plane satisfy the condition. Any further increase in radius adds nothing new to the ball. It may seem absurd to talk about open balls of functions, but not only is the supremum open ball a valid mathematical construction, it is also easy to visualize. In this case, the center of our ball is the function g in red. Then the supremum metric ensures that all functions in the ball deviate by less than r away from g. This forms a sort of tube where all of the functions inside this tube form the open ball. This last result is going to show us why choosing your metric is so important. In real analysis, a function is continuous at a point A if for every epsilon larger than 0, there is a positive delta, such that whenever x is within delta of A, f of x is within epsilon of f of A. This rigorously captures the idea that small deviations in the input should also lead to relatively small deviations in the output, irrespective of how much we zoom in. Now look at the metric space definition of continuity. I encourage you to pause for a moment. It is very similar to that of real analysis, just that we are now mapping between two arbitrary metric spaces, and the absolute values have been replaced by the metrics of the domain and the codomain. Our sense of distance now depends on the metrics we choose, and I'm about to show you a very odd consequence of that. Let the set x be arbitrary, but endowed with the discrete metric. Then let the pair y dy be an arbitrary metric space, f an arbitrary function mapping from x to y, and a an element of x. Given some positive epsilon, can we find a delta such that the metric definition of continuity is satisfied? Surprisingly, despite knowing nothing about the sets or the function, the answer is actually yes. To see this, choose delta to be a number smaller than 1, say half. Then, x is within half of a in the discrete metric, but the only point satisfying this is a, so x equals a. It follows that the distance between f of x and f of a measured in the codomain is equal to the distance from f of a to itself, which is equal to 0 by the first axiom of a metric. Epsilon is larger than 0, and so continuity is satisfied. Therefore, when we map from the discrete metric space to any other metric space, every function is continuous.